All right, welcome, data detectives. Today, we're going to grab our high-tech magnifying glass, which is, math, to uncover some really cool hidden patterns in data. Our mission? To model the real world and maybe even make some predictions about the future. So, let's dive right in. So, you might be asking, how in the world do we do that, right? How can a bunch of numbers and equations act like some kind of crystal ball? Well, that's the big mystery we're going to solve together today.
Okay, so the first thing every good detective learns is that the real world, it's messy. I mean, data about population growth or how popular a new video game is, or even just how fast kids grow, it almost never, ever falls into a perfect, neat little straight line. And that, my friends, is exactly where our investigation begins.
Just take a look at this. We've got a table here showing the heights for kids at different ages. And you can see, right, it's not perfectly consistent. I mean, look at age 3. We've got 2 different heights listed. This is exactly what real data looks like. You can't just connect these dots with a ruler and call it a day. Nope. We need a much more powerful tool to find the real trend hidden in there.
So, if the pattern isn't a straight line, then what is it? Well, our first step as detectives is to start searching for clues. And we're looking for clues that point to a very specific kind of pattern, an exponential one.
Okay, let's check out our first piece of evidence. We're looking at the minnow population in a pond. So in year 0, we start with 1,000. A year later, it's 1,200. Then 1,440. Do you see it? The jump from year to year isn't the same. It's not like we're just adding 200 each time. There's definitely something else going on here.
And that is our big clue. Whenever you see a pattern that isn't just adding the same number over and over, your detective instincts should kick in and say, hey, maybe we should check for multiplication. So let's try it. What happens if you divide 1,200 by 1,000? You get 1.2. Okay, what about 1,440 divided by 1,200? Whoa, it's 1.2 again. Bingo, we found the pattern. This little secret number has a name, and it's called the constant multiplier. This is the smoking gun, the key piece of evidence that tells us we are absolutely looking at an exponential trend. Finding this consistent factor is how we confirm our suspicions. And for our minnows, that magic number was 1.2.
All right, now we know what to look for, but how do we actually build a model without doing a ton of boring, tedious calculations by hand? Well, this is where we bring out our super tool, Desmos. Just think of it as our own personal high-tech data analysis lab.
And using it is surprisingly simple. First, you just feed it your clues, your data points, by putting them into a table. Then you give Desmos this one little special command. It looks kind of weird, but it's just telling the tool, hey, find me an exponential equation that creates a curve that best fits all the data points I just gave you in my table. So you see, our job isn't to be the calculator. Our job is to be the detective who figures out what the calculator's results actually mean.
And speaking of what it all means, Desmos is going to spit back an equation at us. Now, at first glance, it might look like some kind of secret code. But don't worry, because now we're going to learn exactly how to crack it.
So, for this, let's use an example from a town called Crestwood Heights. Let's say Desmos crunched the numbers on its population and gave us this equation right here. Now, let's break this thing down piece by piece and figure out what it's telling us about this town's story.
Okay, first up is this number sitting out front. In the math world, we call this the A value. And honestly, this is the easiest part of the code to crack. It's simply the initial value. The population of our town at the very beginning of the story, back at year 0. So Crestwood Heights started out with about 9,059 people. Simple as that. All right, now let's look at the number inside the parentheses. This is our B value. And hey, does that look a little familiar? It should. This is our constant multiplier again. This number right here holds the secret to how the population is changing year after year. So the really crucial thing to look at here is how this number compares to the number 1. Since 1.07 is bigger than 1, we know for sure the population is growing. But by how much? Well, we just look at how much bigger than 1 it is. That 0.07 part, that tells us the town is growing at a rate of 7% every single year. And just like that, we've cracked the code. Okay, now, before we get too carried away and start predicting lottery numbers, every good detective knows the limitations of their tools.
And a mathematical model, as awesome as it is not a perfect crystal ball. It's super useful, but we have to be careful. And this is a really, really important rule for any data detective. A model is amazing for understanding the trend based on the clues we already have. But the further into the future you try to predict, the less certain that prediction becomes. Why? Because the real world is constantly changing in unpredictable ways. I mean, just think about it. What if a huge new factory opens up in Crestwood Heights? Suddenly, that 7% growth rate could shoot way up. Or what if a natural disaster hits? The whole trend could reverse completely. See, our models are built on clues from the past. They don't understand the story behind those clues. So they can't possibly account for all the surprise events that might happen in the future. All right, team, you've learned how to spot the clues, how to use the super tool, and how to decode the results. I think you're ready. It is officially time to hand you the detective's magnifying glass for your very first solo case. Here it is, your first evidence file. Your mission, should you choose to accept it, is to figure out the story of this local coyote population. I want to know, what was their starting number, and is their population growing or declining? So go ahead, pause right here, fire up Desmos, and see if you can crack this case. These are your clues. All you gotta do is enter these into a table in Desmos and run that exponential regression command we talked about. Don't worry, I'll be right here when you get back with the results. Okay, and welcome back, detective. So, how'd it go? Let's check your work. Your Desmos analysis lab should have given you some parameters that look pretty much like this: an A value that's right around 50 and a B value of about 0.94. Now for the most important part. What does it all mean?
So what's the story here? Well, that A value tells us the initial population was right about 50 coyotes, and that B value, 0.94, is less than 1. And what does that tell us? It tells us the population is going down. It's in decline. By how much? Well, it's 0.06 away from a full 1, which means the population is decreasing by about 6% each year. Boom, case solved.
So, there you have it. You now have this incredibly powerful tool for understanding the world around you. You can model anything from the decay of medicine in the bloodstream to the growth of an investment or even the spread of the next viral video. So the only real question left is, now that you're an official data detective, what mysteries are you going to solve next?